Akiyama from Tokyo, and I am going to talk about tessellability, reversibility, and decomposability of polytopes. And first of all, let me demonstrate something. Here is regular tetrahedron. And if you open this, you will see jigsaw puzzle. Do you understand what I said? Yeah? This is made by origami.
Yeah.
And you cut as you like. This is, yeah, scissors. Okay, and you have to make it flat. So this is a kind of net or unfolding. In order to make this flat, this scissor have to pass through all four vertices. Since otherwise, maybe the three-dimensional part remain. Okay? So I go this. Now something like this, but still here is three-dimensional part. Okay? So we have to continue. We cut this, then we have like this. But here is still small part. Okay? And cut. Okay. Now, completely flat. Okay? Since I put this paper 5 layers, so I have 5 congruent domain. One is brown, like this. Okay? And the second pink, and gray, and red, and yellow. So these are all congruent. And of course, there will be infinitely many different kind of shape. But all of that tessellate or tiles the plane without making any gap nor overlap. So I brought magnet from Japan, but this is not metal. I found. So let me do it here. I said in the beginning, you will see jigsaw puzzle. Okay? So here, red one, and the blue one here, and here is concave part, and you can put like this. Okay? And yellow part, maybe come out. No. This will match. No? Yeah? No? This is easy, but there. Maybe like this. Okay. Something like this. And you can extend this. Infinity. Did you see? So the first several, maybe I can show you by computer graphic. So this is, you can say this in the following theorem. Every net is unfolding or development. Every net of that was a regular tetrahedron tile the plane. No matter how you cut. So, for example, I have already cut. This is regular tetrahedron. And I have already cut here just here, like this, like this. So this is one knob net of a regular tetrahedron. And maybe there is something like this. Okay? And I have many copies. Okay? And here, copy, 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 copy. Too many copies, so I have no time, so I will. Then, of course, you can type like this, and here is dog, like this, and here, like this, and this concave part, you put which one? This one. This one fits here. Okay, and here something like this. Okay, so this is a kind of tile maker, producer. Okay, and so please remember this one. And the second thing is reversibility. Reversible is this. Here is P. Okay, and this one is called truncated octahedron. And this is a kind of parallelohedron. Okay, and the peak is on the bar, and this circle then change to ham. Okay? And this is cuboid. This is box. So this is simply connected. So no hole inside, no empty part inside. Okay, so truncated octahedron change to cuboid. I will show you another example. So in order to explain the definition of reversibility, so this will change to, this is rhombic dodecahedron, because there are 12 rhombus face. Okay, 12 face, each of the face is a rhombus. Okay, and I dissect this into finite number of pieces and reverse. Okay, so inside out, outside in. Okay, I put this is fox. Okay, fox has a tail, and I put this tail, then it will change suddenly to green snake, like this. Okay, green snake. Okay, and this is cuboid box. Okay, and so the second question, at the beginning, tiling, this is jigsaw puzzle. Maybe you're a mathematician. You will ask me, regular tetrahedron is a tile maker. So if you open the surface of regular tetrahedron, then it will tile the plane. Okay? Are there any other polyhedra which have the same property other than regular tetrahedron? So the answer is yes, there are infinitely many other than regular tetrahedron, but all of them are tetrahedron. So if we assume that you have a cube made by paper and cut and open, maybe you cannot tessellate the plane 99.9%, but sometimes it will tile. Okay, and so these things. And the second thing is reversibility. So reversibility is, so if you are given some shape, for example, let me call A, and here is some shape, B, and with the same area, can you reverse A to B? So, for example, I can reverse in 3 dimensions. I can reverse this to cuboid. So the surface of B consists of interior part of A, and the surface of A height inside of B. And this is 3-dimensional case example, but if you see 2-dimensional case. Here, 2-dimensional case. Here is a king. Okay? And dissect this into finite number of pieces to make square, to rearrange and make square. Then you divide it into 4 pieces like this and rotate and become square and bird in the cage, you will see. Okay? There are many examples I brought. So for example, here is what do you a spider. Yes. Here is a spider on the web. And you dissect into 4 pieces and rotate, then you will have geisha girl. Okay? Okay? So I made many artwork. But the essence of reversibility is this. Here is pentagon. And I dissect this along the red line and rearrange, and make, this is hexagon, and the boundary become red. The red one was previously inside. So this is reversible. Okay? So this is the notion of reversibility. And the third notion is decomposability. And this college called Mines, that is a school for crystallograph. And so you you know, there are five convex polyhedra, which copies of which tessellate the space by translation only. Those solid are called parallelohedra, and which was discovered by Russian crystallographer Fyodorov in 1885, and Minkowski proved there are no more five different kinds. So what I found the element, atom of parallelohedron. And atom, the scientists find atom always. Chemists always find element, and number theorist prime number, and the physician maybe the neutrino or quark. And so I like to find the element of shape. And but that is a very big story. So just the polyhedra which fills the space, find the element. And finally, I found the element is this. This one. This one consists of, this one is pentahedron, because there are 5 faces, pentahedron. And 1, 2,